So we had discussed as to how to, if suppose there are n input NAND gates and n input NOR gates, how to actually uh, compute their delay using the logical effort, electrical effort, parasitic effort, and all these things. We had discussed on that. Now let me just continue a little bit about that particular topic. So we said that the normalized propagation delay is equal to P plus G into H. P is the parasitic effort, G is the logical effort, H is the electrical effort, right? And tau is 3RC, the technology constant, which is actually the delay of a unit inverter. Okay, so now if you see, I can say that if suppose I have a gate, any gate for that matter, NAND, NOR or not. Let's take NAND and NOR for now, because whatever we will discuss will hold true for NAND and NOR, because that can have more than one input, right? So if the number of inputs are fixed for a gate, say for example I take a NAND gate, okay, and if I say that it has two inputs, okay, so and similarly a NOR gate which has two inputs, if I say the number of inputs are fixed, okay, and even if I don't specify their sizes, it could be of size k, it could be of size k1 and k2 here, okay, and I don't even know what is k1 and k2, it doesn't matter. As long as I specify the number of inputs, I can know my P and my logical effort, right? These two things I can know. If I specify the number of inputs, then for n input case, we have figured out that the parasitic effort n input, the parasitic effort for both the gates is equal to n, and the logical effort is equal to 2n plus 1 by 3 for NOR gate, and logical effort is equal to n plus 2 by 3 for NAND gate. This is what we had done, right? So if the input is fixed, like say two inputs, then I know my logical effort, my parasitic effort is equal to 2, and my logical effort is equal to 4 by 3 for NAND, and logical effort is equal to 5 by 3 for NOR, right? NOR, NAND 2 and NOR 2, okay. And what about electrical effort? Definitely electrical effort is given by load capacitance divided by its own gate capacitance, the input capacitance of the the input gate strength, or the input capacitance corresponding to the its own gate strength, right? And that is what is electrical effort. So load capacitance by its own gate strength capacitance. Now if I vary the size, it will vary, okay. If I vary the size of the gate, CG will vary, okay. If I vary the number of input, then obviously I am going to vary the input side capacitance, then also this will vary, okay. And load capacitance, sometimes it can be fixed, and depending on the load capacitance, H will vary, okay. So H is the electrical effort, which will vary depending on the gate size. It can also vary depending, and if the number of inputs are varying, then the gate size will obviously vary, okay. I mean the transistor size essentially I am talking about, and that will affect my input capacitance also, okay. And if CL varies, then also my electrical effort would vary. So it makes sense to understand them graphically, okay. So let me just plot a graph, and remember this is a equation of a straight line. So if I plot this as y, and this is something that varies, so this as x, then the plot would look something like this. So which is my electrical effort, okay. H is my electrical effort, and it varies according to CL as well as my input gate strength capacitance, my own gate size, okay. And let me draw it for a two input case, two input NAND and NOR, okay. Then what would be the normalized propagation delay, okay, or normalized gate delay. So let me draw for NAND and NOR, as well as let me also draw for NOT, okay, because even though it's one input, it makes sense to do that because it's always our reference. So the parasitic effort of a NOT gate is 1, and the parasitic effort of NAND and NOR, okay, are, it's actually 2. NAND and NOR gates will have a parasitic effort of 2 if it is a 2 input NAND and NOR. That is what we are considering here. And then these are the intercepts, right? These are the y intercepts, the parasitic effort. Now if h varies, the logical effort is constant, right? That is why it's the equation of a straight line. This logical effort for a 2 input gate is a constant, and for an inverter logical effort is 1. So let us draw a slope like this, and let's call 1 as a logical effort, which is a slope, okay. And then for a NAND gate, this is for a NOT. For a NAND 2 gate, the logical effort is 4/3, slightly more slope than this, so it will be something like this. This is NAND 2 is equal to 4/3, and something like this, 5/3 for a NOR 2. Okay, so this is what it is. So the main idea behind this discussion is for you to understand it graphically. So if you fix a number of inputs, then definitely your logical effort is going to get fixed independent of the gate size, right? And your parasitic effort also gets fixed independent of the gate size. The only thing that can vary is H, or the electrical effort, right? And let's see, then if you have a if you have a series of gates, say for example I have a NOT gate and a NOR gate and a NAND gate, okay, if I go on have something like this, the main thing, if you want to calculate the path delay, okay, path delay, if this is your target, path delay is sum of all the individual gate delays, okay, this is gate 1, gate 2, gate 3, say the sum of all the individual gate delays is the path delay. Okay, if you want to calculate the path delay in such a manner, then you should know first of all how many number of inputs does the NOR and NAND will take, okay, not anyway it is 1, and either you should know, that is sufficient to calculate what, if you know the number of inputs, you can calculate the parasitic effort and the logical effort. These two things can be calculated for all the gates in the path, okay. Only thing that you need to know is H, because tau is 3RC, that is a constant, okay. The only thing that you need to know is H. H is the electrical effort, which is load capacitance by the input gate capacitance. Meaning if I take this gate, I want to know what is the load that it drives, okay, what is the load that is drive this, what it drives, and the capacitance that it sees is the load, and what is its own gate strength of this input, because I said that you always check from one input to the output, you check the path from one of its input of a gate to the output. So at the input, what is its gate strength, okay, or the gate capacitance, that is what you need to know. These two things are needed, okay. There are two ways to calculate it. One is, if you know the size of the gate, then obviously you will know all the transistor sizes. Basically, if you can assume this gate to be a unit size and then calculate the transistor sizes, and depending on the gate size you can scale all the transistors accordingly, and the capacitance will be scaled accordingly. That is one way to figure it out, right? So there are two ways to know H, okay. One is to know sizes of all the gates, okay, if you want in the path, okay, or if you want to know H, I am saying HI, all the H's, okay. If you want to know H of a gate, you should know the size of the present gate and the next gate it drives, which is the load for it. Another way is to directly know the capacitances. If you don't know the gate sizes, that is okay, but if you know this CL and if you know the CG, that is also okay. To know the capacitances, okay, CL and CG of each gate. in the path. Okay, these are the two things that is required for you to estimate H. Okay, if any path is there, so if there is a question to you to calculate the path delay, you should and if the inputs are specified, P and G are easy to estimate, and H will be known either by specifying the gate sizes or by specifying the capacitances at the output and the input of each gate. Okay, so let me clarify one more thing. So what do I mean by CL and CG for each gate? Okay, that is something that might confuse you. If you are very clear, then okay, but still let me just touch upon that so that there is no confusion and clarity established from my side. Okay, so if suppose I take a NOT gate, okay, and I take say I take a NOR gate, okay, like this. If I take this, say it is a 2 input NOR, okay, I have also specified that. So this is nothing but your inverter, and whenever we had drawn, okay, so let me just put this in a box. Say this is the whole inverter block. Okay, this is the inverter block, and this is the next block starts here, let's say. Okay, this is the NOR block and this is the NOT block. Okay, now we know that this particular NOT gate will have an input capacitance, okay, of CG, okay, or it's just basically 3C. Let me write it like this. It's 3C, 2 from here, 1 from here. If it is of size 1, here also let me call it size 1. Okay, size 1. I'll put it here, size 1. This is also size 1. Okay, this is NOR 2, size 1. Okay, 2 input NOR, size 1. Now it has its own parasitic capacitance 3C. Okay, this also we know. Okay, and then about this gate, let me draw it here. It's a NOR gate. So you have series stack of PMOS and the parallel stack of NMOS. Let me call it the input A and the B, okay, which I am not connecting anyway. So A and A are connected. Now I am checking from A to the output path. Okay, so as we know, A has its own input gate strength capacitance, okay, which is nothing but this is of size 1 and 1, this is of size 4 and 4, because the stack, wherever there is a stack, you should scale it. Parallel combination need not scale it. Okay, so this is of size 4 plus 1, 5C. Okay, this is the CG of this NOR 2. Okay, now these two are getting connected. Okay, and at the output you have a parasitic capacitance which is 4 plus 2C, 6C. Okay, I'm drawing it above just to avoid cluttering. Okay, now you have the next stage and so on and so forth. Okay, but what we are saying is that when I say for the inverter, if I want to calculate H is CL by CG, this load capacitance, okay, for this inverter is this CG of this stage. Okay, it is not the parasitic capacitance. Okay, that is something that you should remember. Okay, so because you tend to think that there is some 3C parasitic capacitance here and there is some CG of this gate, so they will get added up. No, it's not like that. This effect of parasitic capacitance had been brought inside this P already. Okay, this P will take care of the parasitic capacitance of each gate. Okay, Now when you are calculating H, it is only CL by CG, and this CL is the load, okay, seen by the inverter, and the load seen by the inverter is a NOR gate, and an input of a NOR gate will have a its own capacitance of 5C, and this 5C will act as a load CL to this particular inverter, and inverter will have its own gate strength of 3C. So H will be 5C, that is the CL for this gate, and then divided by 3C. Okay, this 3C is coming from the input side, this capacitance. This parasitic capacitance should be neglected, okay, because it is something that we do not consider in H, it is being already considered in P, okay, for delay calculation. Similarly, when you go for the next stage, which is, say for example, you have a NAND gate here, okay, this 6C will never be considered in H calculation because already calculated in P, okay. This 6C, which is a parasitic diffusion capacitance of the NOR gate, will not be considered at all in H calculation. It is only the input capacitance of the NAND gate, okay. The NAND gate will have its own input capacitance, and if it is a NAND 2, it is somewhere around 4C, and 4C by 5C will be your CL by CG, okay. That is how it works. I hope this is very clear to you. This is very, very important, okay. Keep in mind, okay.